Hi everyone, let's go over LeetCode problem number 101, Symmetric tree. First, let's understand the problem. We're given a binary tree. We need to check whether or not this tree is a mirror image of itself or not. Let's take a look at this example. Imagine this line is a mirror going through this tree. The root of the tree is a mirror image of itself. Now the problem becomes whether or not these two subtrees are mirror images of each other or not. In order for that to be true, the root of each tree has to be equal to each other. In this case, they're equal. Moving to the next level, the left child of the left has to be equal to the right child of the right. So these two nodes make the first pair of comparison. Next, the right child of the left had to be equal to the left child of the right. These two nodes make another pair of comparison. How do we solve this problem? Intuitively, we would want to traverse the tree and manually compare each pair of nodes at their mirror image position of each other. If they're equal to each other, we move on until we have reached all the nodes in the tree. In this example, first we ignore the root because the root is the mirror image of itself. Next, at this level, we have to compare the left child to the right child. See if their values are equal to each other. In terms of code, that would be left val equal to right dot val. So in this case, 2 and 2 are equal to each other, then we move on to the next level. This level, we have to compare the left child of the left, which is this node right here, 3, compared to the right child of the right, which is this node right here, 3. In terms of code, that would be left dot val equal to this node over here, right dot val. So left, this is the left child, left dot left, which is 3, right, which is this node right here, right dot right, which is this node right here. If they're equal to each other, we move on to the next pair. The next pair is this node and this node. In terms of code, that would be left dot right, left dot right dot val equal to right dot left dot val, right dot left dot val. After we're done with this level, then we can move on to the next level. At this level, if we keep doing comparison manually like this, the problem is getting complicated real quick because when the tree grows in size, the numbers of nodes also grow exponentially. For example, manually, if we compare this node right here and this node right here, that would become left dot left dot left dot val compared to right dot right dot right dot val. Let's trace it to visualize it better. Left dot left dot left compared to right dot right dot right. If we add this pair, 6 and 6, it will become left dot right compared to right dot left. See how the problem is getting really complicated if we keep doing it like this. So how can we simplify the solution? Notice that when we going down to each level, there are similar patterns that are repeating themselves. Look at left, then left dot left, then left dot left dot left. Similar to this side, we have right, right dot right, right dot right dot right. In this case, the best solution would be using recursion. And because we're comparing each pair of nodes at their mirror image position of each other simultaneously whenever we move down to each level, that is depth first search. So this problem can be solved using depth first search and recursion. Let's see how this works in code. First, we need a function that will call itself until we reach the end of the tree. Let's call it DFS, which stands for depth first search. This function can be inside the function is symmetric or outside. Do not forget to call this function. Notice that we skip the root because the root is the mirror image of itself. We only need to check the left child of the root and the right child of the root. What root.left means is the left subtree and root.right mean the right subtree. Let's go over what's going on in this function. Take a look at the first if condition. What if we do not have the left child and we do not have the right child? That's actually the case in this tree over here. We have the root, which is 1. The left child is null, the right child is also null. So right away, we can return true. Don't need to go further. Take a look at the second condition. If not left or not right. So that is the case in this tree over here. Let's say we're at this node. This node is null. This node is compared to this node right here, which is at the mirror image position of this. So if one of the node in the pair has a null values when the other node has a values, then in this case, we just return false right away because this tree is not symmetric. We don't need to go further. How about the third if condition? Now, let's go back to the big tree, a tree to be symmetric. First, when comparing the two subtree, the parents of each subtree has to be equal. So now we're checking for that. This is the left subtree, this is the right subtree. So if left.val, which is this node, is not the same as right.val, which is this node, then we can return false right away. But if they are equal, we can keep moving forward and comparing their child, which is this subtree, and this subtree, and then this subtree, then this subtree, and so on and so forth, until all the node in this tree has been visited. Now is when the recursion is happening. The function is calling itself. This is the first call. This is the second call. First call, now we're done with this level. This call moving us to the next level. Here, this parameter left is replaced by left.left. We have left, we have right over here. So left.left, left.left, we're at this node right here. Right.right, right.right, we're at this node right here. We're comparing these two. So none of these nodes have the values of null. So the first two conditions we can skip. Now we're comparing the values of the parent node of this subtree and this subtree, which is 3 and 3. If they're false, we can return, if they're not equal to each other, we can return false right away. But in this case, they're equal to each other. So we keep going. How about the second call right here? Left.right. Left.right means this node right here, which is 4. Left.right. Right.left is this node right here. Or in other words, we are comparing this subtree and this subtree. So again, because none of the node we're looking at is null, so we would skip these conditions. Now again, we will compare the values of left, which is 4, and the values of right, which is also 4. They're not different from each other, so we cannot return false. Let's keep going. Now we're done with this level. We can move on to the next level. Each time the function calling itself, we're comparing each pair on the left and the right of each subtree until all the nodes are visited. If the nodes in each pair are equal to each other till the end, we can return true, which means the tree is symmetric. What is the time and space complexity? So because we traverse the tree and visit all the nodes, that would be O(n). Space complexity would be O of h, where h is the height of the tree. Let's submit the code to see if it works. Cool, it works. Of course, because I double-checked this multiple times before recording. Even though recursion is the best way to solve this problem, there's another way using queue to implement the same logic. A queue follow first in, first out operation. Let's look at the code. First, let's check the edge case. If there's no root, we can return true right away because the tree is automatically symmetric. Now initiate an empty queue, add root.left and root.right to the queue. Remember that root.left is the left tree, root.right is the right tree, not just the values of each root. I'll just write 2 for short, so this is the left tree, and this is the right tree. Now we're at the while loop. This while loop will run until the queue is empty. Let's pop the 2 subtree that we added earlier and compare them. First, left, let's call it left, this is right. Pop this one, and remember this is the whole subtree, it's not just the value of 2. The right, we also pop this one and compare these. If these are the same, if the values of the root of this subtree is the same of the values of the root of this subtree, then we can move on. Otherwise, we return false, which is actually this condition right here. What are these 2 doing? So for this if condition, if not left and not right, continue. This happens when, let's say, we're at the end of the tree. The values at the end of these nodes will be null. Let's say this is null, this is also null. That means if not left and not right, for example, here and here, if they're both null, that means we're done with that path. Let's continue with the remaining path. How about this condition? In this condition, if not left or not right, for example, if we're at null over here and this node here, there's a value, so null is different than this value. In this case, the tree is not symmetric, so we return false right away and break this loop. Now that we're done with the first comparison, let's move on to the next. Let's append left.left and right.right subtree to our queue. Left.left means left.left, which is this subtree. Right.right means this subtree. I'll just write 3 for short. This is the left subtree, this is the right subtree. How about left.right and right.left? Left.right is this subtree, and right.left is this subtree. I'll just write 4 and 4 for short. Now our loop will continue. Let's go back and pop the subtree that we just added. Let's pop this one and this one. So 3 and 3. Because none of these are null, so we can skip these 2 conditions. Here, because 3 and 3 are the same, we can continue with the loop. When the loop goes on, we're here. Let's append left.left and left.right. Our current left is this subtree, and our current right is right subtree. Left.left is this node, which is 5, and right.right, which is this node. I'll add 5 to the queue. Now we're at this line. Left.right means this node 6. Right.left means this node 6. The loop is continue one more time. Now let's pop from the front of the stack. What do we have? We have 4, 4. Let's pop them over here. Because none of these are null, we can again skip these 2 conditions. Then we're at this line again. Because they're the same, let's move on. Now our current left is 4 and current right is 4. Left.left means right here, left.left, which is this node, 7. Right.right is right.right, 7. Moving on, left.right, which is 8. Right.left, which is this node here, 8. Done with on this line, again, the loop is continue. We keep popping 5 and 5. Since we're already at the end, I would not draw out anymore. 5 and 5, they're the same. Moving on, 6 and 6, 7 and 7, 8 and 8. Now the queue is already empty. That means that this while loop is done. At the end, we can return true. This tree is symmetric. Alright, the last thing to do is to submit the code. See if it worked. Yes, but it's not doing so well compared to the recursion version. That's it for this video. I hope this is helpful. Thank you for watching and happy coding!